Okay, my name is Eugenia. My last name is absolutely unpronounceable, but it's well correlated with today's topic, the basics of cryptography. Uh, I think that I'm a lucky person because I was able to look at information security and at cryptography in particular from three different perspectives, from the scientific perspective at the university, then from the defensive side, and now from the offensive side. Hopefully it's going to be useful for today. And first of all, cryptography is a very big branch by itself inside mathematics, and only in my diploma, and I was just a mathematical student, was over 500 of hours focused on cryptography topics, and it included a year course only on elliptic curves. So, and the cryptography has a big history. It has been here for centuries. So obviously for today it would be impossible to go very deep into its history or into mathematical background, but I'll try to cover the most well-known terms and algorithms which I use today. I created something like a mind map of the main cryptography topics. I'll try to cover most of them briefly, except for cryptanalysis, because this is a big separate topic by itself. It's very interesting, but it includes a lot of different variations of attacks. They depend on which information an attacker has, which part of the crypto system an attacker can influence, like plain text, cipher text, and with which algorithms they deal. So we will talk only about algorithms themselves. And first of all, initially cryptography was created for confidentiality because there has been a need to hide important information from strangers. But with development, it turned out that cryptographical methods should also solve other tasks like authentication, integrity, non-repudiation. And an important principle in cryptography, since we are talking about a scientific branch, that the security of a crypto system must depend only on safety of the key, not on secrecy of the algorithm itself. The information about algorithm should be public, and it shouldn't affect security of the encryption scheme. So there is a difference with, for example, steganography. And we will start with the most classical cryptography type, symmetric cryptography, which appeared first. It's called symmetric because there, for encryption and for decryption, the key used, they can be derived one from another, and actually you can consider it as one key used both for decryption and for encryption, because it can be easily calculated, and that's why it's called symmetric. And inside symmetric cryptography, there are two types of ciphers. The first ones are stream ciphers, which deal with your plain text one unit at a time. Nowadays, unit is usually a bit, but previously it was, for example, a character of an alphabet. And the most classical and old and well-known example of such a cipher is Caesar cipher, which Caesar used to communicate with his generals. When an alphabet is moved 3 characters forward, so A becomes D, B becomes E, and so on and so forth. And when you apply this algorithm to your plain text to encrypt it, you can apply it 1 character at a time for the text of any length. On the other hand, there are block ciphers, which deal with blocks of a certain size. And this is the main difference between them. We'll start with stream ciphers. And the most important arithmetic operation, not only in programming in general, but also especially in cryptography, is exclusive OR. XOR, its truth table is on the left, and it's especially important in cryptography because of its property that any value XORed with itself always gives 0. So the typical stream cipher, they have the same structure. You have a plain text, and you have some key stream generator, which generates a key stream, one character at a time. And these characters are XORed with your plain text. So when the other side want to decrypt your plain text, they have the same the same key stream generator, and when they XOR again the key stream with the cipher text, it turns out that they have two key streams XORed, which gives 0, so they receive their plain text back. So it's a very important property, and the security of stream ciphers is based on security of these key stream generators. You can believe it or not, but a perfect encryption scheme actually exists. It's a stream cipher called one-time pad, but you probably never heard about it unless you studied cryptography, because it's just a theoretical model, because in this scheme, key stream generator must be truly random. So it should be absolutely unpredictable, and in fact it means that your keys must always be of the same length as your message, which can have different lengths, and it's absolutely ineffective on practice. So on practice, there are pseudo random sequence generators, which are used as key streams to generate key streams from a limited size key. And security of stream cipher strongly depends on these pseudo-random generators. The most well-known stream ciphers are RC4, used, for example, in wireless web protocol, and A5 used in GSM communications, but both of them are considered to be insecure, especially web, and a part of it because it's really difficult to correctly implement a stream cipher. Also, they are fast and they can be useful. It's difficult to create this randomness. Take into account that your generator is pseudo-random. It's difficult not to repeat the same key, and once the key is repeated, the stream cipher is compromised. So it's much more difficult to implement this stream ciphers on practice rather than block ciphers. So about block ciphers, they deal with blocks of a certain limited size. The block size depends on the encryption scheme you use, and since the block size is fixed, we need to apply padding sometimes in case if your data is less than the length of the block. And padding is just when we add some additional information to the end to our text. It can take different forms. There are different standards for it depending on the context with which you are working. For example, one of the standard paddings is adding the number of bytes, which you use for padding. And another one is just complementing with zeros. But an important requirement that padding must be reversible. And for example, if you add zeros, then your initial text must not contain 0 bytes, because otherwise it would be impossible to recover the text and distinguish padding from your real text. An interesting attack related with the padding is so-called padding Oracle attack, and it has nothing to do with Oracle databases. Actually, it's I like to ask this question at job interviews when someone starts to tell you about Oracle databases. It means that they don't know about this attack. This is when a vulnerable system responds you whether padding in the text it receives is correct or not. And based on this information, depending on the encryption scheme, it's often possible to decrypt this cipher text one by one, byte by byte, and it's actually a very practical attack in many cases. For example, in
Yeah, that makes sense, because you know that the message is shorter, then you have less than the
the message is not necessarily shorter. I will.
The crypted text is shorter, so you have less to attack, right?
No, it's always dividable by the size of the block. So we add padding, then we encrypt it, and so we send it to a vulnerable system, but we change just 1 byte in the end. And its response, if it discloses information, whether in the decryption attempt padding was incorrect or not, you can, based on this information, recover plain text. This is very practical. Like in 2010, there was a vulnerability in ASP.NET, which allowed to read sensitive file from the web server. And this is exactly this vulnerability related with cryptography implementation. Since, again, we have to deal with blocks of limited size, we don't only have to think about what to do if our text doesn't fit with this block size. If it's smaller, we have to think about what to do if it's larger, because actually block sizes are usually small. And for that, different modes exist, how to combine all these blocks into the cipher text. And I'll tell about all these abbreviations a little bit later. And so there are different approaches to that. The most well-known ciphers are DES, it's upgrade triple DES, AS, Blowfish, and let's start with DES. DES is an abbreviation of Data Encryption Standard. It's very old. It was created in 1970s. Its block length is 64 bits. Its key length is also 64 bits, but some of them are used for parity checking. So in fact, effective key length, which is actually used for encryption, is 56 bits. It has 16 routes of encryption and is used in different other protocols and algorithms, which you probably meet very often. Here is the basic picture from Wikipedia how it works. It starts with initial permutation. Permutation is just when you have a certain set of characters, a certain set of objects, and you just shuffle them somehow according to certain rules. You do not change them with anything else. You just mix them. Then actual encryption happens in 16 rounds, and then there is an additional final permutation, which gives you an encrypted output. Actually, these initial and final permutations are just legacy. They were needed for hardware at the time when the algorithm was created. The most interesting part is the encryption part in the middle. When DES works with,
Did anybody ever determine in the S boxes in DES whether or not, why they made the decisions they did for the S box, you know, how they, what was contained in them? Because I don't think they ever came out and said really why they made
I don't know details. It's just there must be non-linear and it must be not easy to recover it back.
Just curious, it's a minor thing, but it had been years since they put out that algorithm, and
Yeah.
They never explained why, they put out the algorithm, they made it public.
Yeah.
But they never explained what the S boxes were, why they made the decisions they did for the number, the contents of it. Why do you do this shift in this way? They just said,
Actually,
"Yeah, just do it."
in Russia, it's much more much funnier because there is a somewhat analog algorithm called GHOST appeared almost almost at the same time, and so use somewhat similar approaches. It also has S boxes, but their boxes were secret and must be given to you by a government.
Yeah, I think it was something similar when that came out, but then they made it public, but they just said, these boxes are this way, and everybody asked why, and they went, don't ask. They said so, kind of thing.
Did any mathematicians or cryptographers more on the research side ever look back at tests and try to figure out mathematically why they thought those were good?
It initially was created by mathematicians. There was a competition for that, but it was a closed competition. I don't know, maybe probably someone wanted to do that. So usually there is when there is an interesting algorithm, a lot of people start to analyze that.
Was the Russian algorithm a block cipher as well?
Yeah. It's actually widely used right now because unlike with DES, DES now is deprecated and mostly because of its key length. And back then, they already thought that they were paranoid and thought that we need a larger key length. And they, from the very beginning, they used 2056 bytes. The algorithm itself is pretty close, just a little bit different in substitutions, permutations, but it's better because of the key length.
What is the Russian one called?
GHOST. It's GOST. It's just there is a number for this particular algorithm. It just means it's an abbreviation of government standard. But when you say about GHOST, it's usually the symmetric GHOST, and there is also a symmetric GHOST. So it's it takes this key. And it doesn't use it for every round as is. It has an algorithm to derive subkeys for each round, depending on the round number. It takes, at each round, it takes this subkey containing 48 bits. It takes a half of block of the current text. This half block of 32 bits is expanded to 48 bits as well, and these values are XORed again. And now here we come to this S blocks which we discussed. There are 8 different S blocks somehow created, not to be too difficult, too easy to crack. They create from each 6 bits, they create 4, and we will get back 32 bits, the same length as the half block had in the beginning. This is the most important part because it's not linear, it's created from 6 bits, 4 bits. And then there is an additional permutation which ensures that 4 bits from the same S block will go to different S blocks on the next rounds. And this is this part is called facial function. And this is the basic function of this, and so this is applied to half blocks. Then this half block is XORed with the second, the other part of the plain text, and this repeats and in 16 rounds. With this, the decryption process is the same as the encryption process. This is useful. And nowadays, this is considered to be not secure anymore, and not only because different attacks were found, they just make attacks a little bit more effective than brute forcing the key, but because of the key length, as I already said, and there are cloud services out there which you can use to crack these keys simply by brute forcing this key. And it's useful, for example, if you have NetIntelli version 1 hashes, if you are not afraid to upload them there. There was an upgrade in the end of 90s. It is called 3DES. There are different variations depending on how 3 keys used at different stages are derived. Either derived from 2 keys, DES keys, or from 3 DES keys. And it's just DES encrypted, decrypted, and then encrypted again with 3 different keys. So the key length is not such a big problem anymore. But in 2016, there was an attack found against triple DES called Suite 32, which allowed to partially recover small pieces of plain text, and which is becomes especially dangerous when you have a big amount of data encrypted. Yeah.
What was that attack called?
Suite 32, a birthday attack. So because of that, in 2017, it was announced that triple DES is also to become deprecated, and it already shouldn't be used to encrypt large amounts of data, like when you exchange information with different systems by TLS, IPsec, or when you encrypt large files. And soon it will be deprecated at all. But luckily, since the beginning of 2000s, there is another standard out there, advanced encryption standard, and in fact, now it is a standard for symmetric encryption. Nowadays, there are no any effective practical attacks against AES. It has a larger block length, 128, and different key lengths and different number of rounds depending on the key length. And it's widely used in a lot of different protocol systems. You can meet it in TLS, SSH, IPsec, and many, many others, because it's de facto standard. And it's quite good for now. I already mentioned different modes which can be used to combine different parts of blocks of encrypted text. And let's talk about them a little bit. The first and the simplest approach which you can think about when you need to combine different blocks is simply encrypting them independently and then just concatenating back again. But this is a very bad idea, because when you encrypt the same plain text with the same key, it would be obvious when you have the same pieces of plain text from your cipher text, if the block was the same. The blocks are quite small. So there are different attacks on electronic codebook, and so it shouldn't be used. It discloses too much information, especially if you are trying to encrypt some predictable data, like some protocol inside with headers, known headers, and so on. So there are other approaches to deal with it, and the next approach is cipher block chaining, is when you exert the current block with the previous encrypted block. So it creates turbulence, create an additional problem for an attacker to analyze it, to understand whether this block was the same in different plain texts. And here the question arises what to do with the first block, which doesn't have the previous one. And for that, there is the so-called initialization vector, which is given as an input for the first block. And for its generations, there are also different approaches, because if you have it a constant initialization vector, it's basically the same as having an electronic code boot, but only with the first block, because it would be obvious when you have had the same plain text. So there are different approaches to generate this initialization vector. It can be generated by a pseudo-random generator. It can be some kind of a counter, and so on. The other modes are output feedback mode. It's pretty close to cipher blockchaining, but it's like creating a stream cipher based on a block cipher. So instead of encrypting using the encryption scheme to encrypt the plain text itself, it encrypts the keys. So at first it takes some initialization vector 2, and then it encrypts with your master key. Then for the next blocks, it encrypts the previous block, and so on, something like a Russian doll. And then plain text is just XORed with the resulting key stream. Another example, which also de facto creates a stream cipher from a block cipher, is a counter mode, but it doesn't create recursion of encryption. On each stage, for each block, it encrypts some temporary, for this session, number nonce concatenated with the number of the current block. In both of them, it's very important, extremely important to initialization vector or nonce to be unique every time, because here we again have to deal with pitfalls of stream ciphers. As soon as you encrypt the same data with the same key, you encrypt different data with the same key, an attacker would be able to XOR these two cipher texts. These key streams would get 0, and you would get information about two planes XORed with each other. And if an attacker was able to affect one of these plain texts, then an attacker would be able to completely recover the other one. Here, uniqueness is extremely important, and again, it's maybe difficult to in real-life implementation when you have a limited amount of memory and so on. All these methods of encryption, they are focused on confidentiality, but don't take into account integrity and authenticity. So for this reason, there are other important features in cryptography, like hash functions. Of course, everyone heard about them. In general, a hash function is just a function that takes an arbitrary long input and then produces a fixed size output, a message digest or a fingerprint. But in cryptography, it has a special meaning, and in cryptography, it's actually, when everyone talks about hashes, it actually means these cryptography hashes, which is different, for example, from a checksum like CRC32, because there are additional requirements. Is that this function must be one way. It must be, if you're given a hash value, it must be difficult to recover the initial text. And it also must be collision resistance. Collisions is when different messages have the same hash value on the output. And since the hash value is of limited size and there are infinite messages possible, there are always a lot of collisions around. But the collision resistance means is that it's difficult to find these collisions. It's difficult to find the second message which gives the same hash value if you're given a hash value. And it's also difficult to find two different messages which result in the same hash value. So those are the most important properties of cryptographically strong hash functions. And there is also an additional requirement, desirable property of a hash function, more derived from practice rather than from mathematical field, is that it shouldn't be too fast. Because, for example, if hash value, hash function is used to store passwords in a database. When you're a user of a web server with this database, when you try to log in into your account, you present your password, the system processes your password, creates a hash, compares it with the value in its database, and if everything is fine, you are logged in. So system works with one or several users at every time. And from your side, you always, it's not a big deal if you have to wait for extra second. But if an attacker compromises the database of this web server and receives all the hash values, for them it would be harder to create a lot of different hashes if the function is not too fast. So it will help to make the life of an attacker harder. This is a desirable requirement, a desirable property, but not a strict requirement. There are a lot of examples of hash functions, MD4, MD5, different SHA functions, but the first three of them are already considered to be insecure, especially MD4 and MD5, and because collisions were found, algorithms to find collisions exist, and also some of them are very fast. So it's better to use SSH2 family. A term which is closely related with hashing is cryptographic salt. One of the reasons why it exists is so-called rainbow tables. Is when a rainbow table is a list of pre-calculated hashes for the most widespread passwords. Even if the hash function is not too fast, an attacker may invest their time and resources into pre-calculating on this big list of hashes for the most widespread passwords. And once he gets hashes from a compromised system, they simply quickly search for the same hash value and know that this value corresponds to this particular password. And cryptographic salt is used to solve this problem. So it's just a random string which is added to a password before it is being hashed. And even if two users have the same password, or even if this password exists in a rainbow table and it's not too strong, then for an attacker it would still look different. All these passwords would still look different, and an attacker would have to recalculate a hash every time with the salt taken into account. It makes an attack more difficult, and it also doesn't disclose information that several users have the same password.
So when I create a user, I just create a random salt for them and I keep it for the lifetime of that user for eternity?
No, you can change it usually when you create, like in a Linux operating system, when you create a password, it automatically creates a random salt. It's added there.
So
yeah.
if they don't use their password, they're going to do.
And a small upgrade over the hash topic is method authentication codes. They are somewhat similar to hashes. They're also used to provide authenticity, but in this case there is a key, and only someone having a key is able to check the message authentication code. With the hash it can be done by everyone. And there are different approaches to create this message authentication codes. The first one is cipher block chaining mech. As you can imagine, if we are talking about keys, we can just use some block encryption for a different purpose, a little bit change it. And this is actually what is used with CBC mech. You just encrypt the message just you simply just encrypt the message with an algorithm you use, and then take the last block or even the half of the last block to use as a message authentication key. There are different pitfalls, tricks related with usage of this particular approach. When you just look at the formal description, you may not notice them. For example, you must not use the same key in the message CBC message authentication CBC MAC if you are also using at the same time CBC encryption. There are also so-called length extension attack, when an attacker can add malicious blocks inside the text. So in fact, here you must encrypt not the initial text by itself, but you also should add there the length of the message to be able to protect from these attacks. But when it's implemented correctly, it's a good approach to add authentications to communications. Another approach is based not on encryption, but on hashing. And it's called HMAC. It's a specially created formula with which depends on the message and the key. And simply hashing of message concatenated with the key, it has own vulnerabilities. And this is specifically adds some padding and additional round of hashing to avoid weaknesses related with the most simplest approach when you just combine message key and hash. It's called HMAC. And message authentication codes are used to improve block cipher modes. There are also approaches which initially combine encryption and authentication. So MAC is already included into the encryption scheme. It's Galois counter mode and counter mode, which we already discussed previously, but with CBC MAC added. In particular, it also can help to protect from padding oracle attacks, in addition to not disclosing information about padding status, detecting that the cipher text was changed also helps to prevent such attacks. Finally, about symmetric cryptography, it's very effective. It can work with big amounts of data. It's fast and it's very useful. However, it has its own disadvantages, and the main of them is key management and distribution. If two sides must have the same pre-shared key, they must, before exchanging encrypted information, they must share this key somehow, and if they don't have a secure channel between them, there would be a problem. Also, there became a problem if you need to have a separate key to communicate with each person, so you have to collect all these pre-shared pairs, and it's also a problem. That's why asymmetric cryptography appeared. And the difference between symmetric and asymmetric is that in asymmetric cryptography or public key cryptography, you cannot derive the decryption key from the encryption key. So it's safe to publish the encryption key, the public key, and keep the private key for yourself, because no one would be able to get it from the public encryption key anyway. So to encrypt a message with this approach, for example, if you want to encrypt a message for me, you take my public key, which is available for everyone. You encrypt a message, send it. It's not a big deal if it's sent it over an open channel. And it's only me who would be able to decrypt it, because it's only me who has the private key, and no one would be able to derive it from the public key. A little bit of mathematics behind what does it mean that it cannot be derived from, or what is easy, or what is difficult. In the complexity theory, there is a class of decision tasks, decision problems called P, which are solved so-called easily. Easily means that the time to solve these tasks on a deterministic Turing machine is a polynomial from the size of the input. We will not go deep into the formal definition of the deterministic Turing machine. You can think of it as of one core computer with infinite memory, but which can work with one unit of memory at a time and has only a finite set of instructions what to do on the next step. For example, if you have, and this complexity is denoted as big O of some function from an input. So for example, if you have a simple program writing hello world and that's it, this program has a constant time, it doesn't have any input, it will have a complexity big O of 1. If you add input n to this program and you create a cycle of n times repeating the same printed message, the time of work for this program would be linear, depending on the n that you give in the beginning, the number of cycles to do. So it would be big O of n. If you get create another cycle of the length n within this cycle, so it would be n squared, and this would be big O of n squared. So similarly, with it's a number of steps depending on the size of the input you have, problems which can be solved in a polynomial time on such a machine, they're considered to be easy, even if the power in the polynomial is big. On the other side, there are other problems where if you are given a solution to this problem, you can verify that this is actually a solution in a polynomial time, just like with P. But we don't know if finding a solution requires polynomial time or not. Obviously, the class P is inside NP because if you know that the way to find a solution is simple, is easy and fast, then this is also a way to verify a solution. But this is a huge question whether P is equal in P. This is, yeah?
Oh, sorry. I'm not so great at math, so just the n being in the exponent is sufficient for that not to be polynomial time. Right?
We are talking about the best of known algorithms. So, if the best algorithm known for now to solve problem has exponential time, we say that this problem has exponential time. But we don't know. Maybe there is more effective algorithm, but we haven't invented it yet, which will do it in a polynomial time. And that's why this is a problem. There are tasks for which we know not effective algorithms, but we don't know whether there are effective algorithms.
Oh, I was just asking, so for P, and if we say that in an amount of time that is polynomial in the size of the input, so like n raised to k, that would always be an example of P,
yeah.
Because there is no k that will make that not within the realm of P. But then anything that is like 2 to the n, where the n is now part of the exponent, that would not be part of, it would, if we assume
the
that P
basis,
is not
and
equal
here
to
n is exponent.
Okay.
And it's not necessarily exponential, it's just can be something more difficult than polynomial.
Okay.
Yeah.
Okay, thanks.
It has to do with how quickly the function grows.
Yeah.
Yeah. So there is a big question whether they're equal or not. If you solve this problem, you would receive you will be awarded. And classical asymmetric cryptography for now assumes that it's probably no, that there are NP problems for which solution can be checked quickly, but at the same time we cannot quickly solve the problem itself. For example, the problems which are actually used in public key cryptography and which help to understand the difference between P and NP is that if you have a big integer number which is known to be a product of two prime numbers are those who don't have any divisors except of 1 and themselves, you should find the pair of P and Q which multiplied give you N. So if someone gives you just N and asks you to find this P and Q, unlikely that you would be lucky enough to do it quickly. If N is large, probably you would try one prime number after other until you meet P or Q, so it's going to be exponential time. But if you are given N separately and P and Q separately, and if you are asked whether P multiplied by Q is equals to N, it's easy. You can just multiply them, compare, and that's it. It requires polynomial time just for multiplication and comparison. So it's easy to check, but it's difficult to find the solution when you are given only the task. Another problem used in public key cryptography is discrete logarithm. It's working over the multiplication group over some modular. Modulus arithmetic is simply when you have a certain modular and you are not allowed to have any numbers except from 0 to p minus 1. And if there is anything bigger appears in arithmetic operations, then you take only the remainder after dividing this number by p. So here all the operations are given in this finite group. And the problem is that when you're given this modular, you are given some number called generator, and a number which is known to be a generator to the power of something by modulo of p, you should find this exponent value. So this is a logarithm. And this is known to be a difficult task. It also belongs to NP. And a variant, it has a huge mathematical background underneath, but the approach is mostly the same, that elliptic curves, points on elliptic curves, they also can form a group, a finite group. You can also define operations in this group, and for these operations you can state a similar problem, but only for a very specific group. So how public key cryptography approaches solving the problem of the symmetric key cryptography, such as key exchange. In 1970s, Diffie-Hellman presented the approach to that, and nowadays this is actually the widely used approach to do that, named after them. It is based on a discrete logarithm problem. So we have two communicating parties. Both of them know the prime number and the generator. This is public information, so anyone can know it, and it's not a problem. Each of one generates their own number, which should be kept private. And they take the generator to the power of their own number by modulo p and exchange this information. If an attacker is able to listen to this channel, all they get is that this information, when the generator already is taken to the power of some private numbers, and this is exactly the discrete logarithm problem. So to solve it, to find the initial secret numbers, an attacker would have to solve it, and for now we don't know effective ways to do that. Once the legitimate parties receive this information, they simply put the received number to the number to the power of the number again, and so they get the same result, g to the power of xy, and so they can use the shared secret for further communications with symmetric cryptography.
I think for this system, there's also another scenario where you'd use the private key to prove your identity to people out of the public key.
It will be a little bit later. Yeah, it's about digital signatures. Here, it's about key exchange. And actually, the part with digital signatures and in general authentication and trust is very important here as well, because if an attacker is able not only to listen to the channel but also to interrupt communications and pretend to be any of the other side, if an attacker is able to perform a man-in-the-middle attack, then the scheme becomes vulnerable. So there should be another way for each of the recipients to ensure that they are talking to the right person before exchanging the keys. And for that, digital signature recipes, public key infrastructure exists, the different third-party trust centers to ensure that you are talking to the right person. Another application of public key cryptography is encryption. The most well-known scheme is RSA, named after its authors, Shamir and Edelman. And this scheme is based on prime factorization, which we also already discussed. And the public information in this scheme is this some big number, which is a product of two prime numbers, and the encryption key itself. This is public key, which should be relatively prime to this special number based on P and Q. This is chosen, this and how private key calculated, this is chosen because of specific properties of modular arithmetic in order to make description and encryption possible for every message, because when they are chosen in this way, after you get an encrypted message with your public key, with E, you apply your private key D to that, and after that, it always will get you back the initial message. So those requirements are to make encryption and decryption possible. What's important for the public cryptography side is that to be able to attack this scheme, to be able to get the private key and compromise this scheme, an attacker would have to factorize the n to find the numbers p and q, knowing only the n, and this is exactly the prime factorization problem, which is also known to be NP. Once you have an encryption scheme, you can, with public key cryptography, it's usually with little bit changes, can be used for digital signing, which are used for authenticity. And the process is somewhat similar, but a little bit, but private and public keys are used in a little bit different ways for encryption and decryption. So if you want to sign the message for someone, you publish your public key is again available for everyone. You take a hash sum from your message, then you encrypt it with your private key. It's only you who can do this, because no one else has your public key or private key. And when the recipient receives a message and a signature, they decrypt the signature with your public key, which is available for everyone. And if the hash is the same as in the initial message, they can conclude that it was you who actually signed it, because only you was able to encrypt it with your private key. No one else could derive it from your public key. So for RSA, there is also a scheme to use it for digital signing, not for encryption. The most widespread algorithms, we actually already discussed them. There are not so many out there. It's RSA, it's Diffie-Hellman for key exchange. There's also digital signature algorithm for specifically to create digital signatures. And there is also elliptic curve cryptography, which has its own specific, but the basics, the approaches to decryption, the encryption, and signatures are pretty the same, like it's the same for public key cryptography in general. And how it is combined together, probably you noticed when I talked about AES, which is a symmetric cipher, that it's used in SSH, in TLS, in PGP, as mine. But if you ever use those protocols, you already notice that there are public keys, so there is not only symmetric encryption, but you probably notice there is also asymmetric public key encryption there. And here is, for example, how TLS 1.2 works. At first, the client sends information about which ciphers they are going to use, which protocols they are going to use. And so all these abbreviations are already familiar, like DHE, it's a little bit modified, but basically the same Diffie-Hellman for key exchange, RSA for digital signing, AES 256 for further encrypted communications. It's used, AES used in cipher blockchaining mode, and SHA 256 is used for hashing. So then the server creates the parameters of the Diffie-Hellman scheme. Then they take a hash from these parameters and sign it with RSA and send all of these parameters, the signature and a certificate with its public key to the client. The client checks the certificate. Certificate, it's something, it's simply the server's public key, digitally signed by a trusted party, by a certification authority. So this is another application of digital signatures. And the client checks that whether they can trust this server or not. Usually, if we are talking about browsers and TLS here, they just have a list of trusted certification authorities already included into their operating system. If this certification authority in this list, then this certificate can be trusted. If it's not, you will see the message that this is a suspicious certificate. And if the client decides that they can trust the server, they generate their part of Diffie-Hellman scheme parameters, send them back, and now they both have the same pre-shared secret, which further can be used for AES encryption in cipher blockchaining mode. So all of that are used in the same protocol. Pros and cons of different encryption schemes, hashing and digital signatures are combined. That's it. Hope it wasn't too long or too boring.
Can you recommend a book so that we can learn more? Like from this level, like an introductory book?
Bruce Schneier's books are actually good. This is now, I don't know now whether he works with cryptography or not just blog stuff, but he wrote a lot of books, and many, like Ferguson, together with Ferguson, is a good one to applied cryptography, and there are different editions of them with a lot of practical overviews, so including mathematics. And they also give a lot of additional information like history of different ciphers, or some ciphers which are now not popular, but maybe it would be interesting to read about them.
What is his name again?
It's different books of Bruce Schneier.
Thanks.
So I wondered with the RSA algorithm, so when they create the 2 primes, or you select the 2 primes, finding prime numbers by itself is a relatively difficult problem. So when they do that, where do they get the source of the primes from? Do you know?
They just take 2 primes and they just multiply them. So this is the easy part. The
So they have a
difficult.
list or something?
Huh?
They have a list of prime to use, or?
For like key generation.
Yeah,
Like how
the
do
key
you how do you
generation.
get the initial prime? Like if
Yeah.
I was to go get a certificate from like DigiCert or something, they have to make a huge prime number, right?
Oh, no
Yeah.
idea.
I guess that's the question I'm kind of wondering,
Yeah,
like,
how many-
that might be exploitable.
I don't know.
How many prime numbers do we know about, and like how expensive is it for us to find the next one? Because I thought that finding more and more prime numbers
Yeah, it does get
was
harder.
more and more expensive, yeah.
With RSA, the length of the numbers is limited. This is you have to choose the length which you are going to
Okay.
use. Now, previously it was allowed 124 bits. Now it's already considered to be deprecated soon. Now it's RSA 248. But still this length is fixed, and so within this length, I suppose it's not such a big problem to find the prime numbers themselves, but it's difficult to find factors.
Right, it's difficult to find out which prime numbers are used,
Yeah.
because you can use algorithms like the ciphers to find prime numbers that are relatively large in pretty quick time.
It seems like a fairly parallelizable task, though, to try to test against
Yeah.
the key. If we're only looking at all the prime numbers that go up to 256 bits or like whatever size,
Hence the problem.
like
Yeah, but
then
the
there's a
problem is
finite
in
number of
yeah,
them.
Determine the prime.
Like we know what all of them are.
yeah.
We can have a big table of them, and then we can take any key that we want.
Yeah, but it's
look
too big.
through all
So
of them.
it's to find the factorization problem solution, you would still have to exhaust them, all of these prime numbers. Not all the numbers, but all of the primes.
Uh-huh.
There's also 2 involved in like a 2-way communication, which makes it even worse.
There was a competition to break RSA for certain numbers of certain length, and so that's why already it's considered to be deprecated to have lengths for 1024.
Okay.
But some numbers of lengths like 700 with something digits were correct, were actually factorized, but were exact numbers under an exact competition, and it took a very long time. So it's still just a precaution to make them larger. Still, even 124 is good for now.
Yeah, I'm not really disputing it. I'm more trying to poke at my own like misunderstandings of like why that wouldn't work, which can't be true. One of the slides was talking about NP hard problems and saying that like certain-
No NP hard,
Oh,
because
sorry.
NP hard, this is a different class of problems.
Okay,
It's,
sorry.
yeah.
We had P and NP,
Yeah,
and then there were
they're like intermediate NP.
okay. There were problems that we could verify the result in polynomial time,
Yeah.
but it would take not like above polynomial time in order to actually calculate the result. Is any of like
Those are
I don't-
incomplete problems.
I don't know if this is just bullshit or if this is a real thing, but is it true that hypothetically like a quantum computer that actually worked would be able to solve those problems because it only has to verify the result? Or like
Verification is never a problem. The problem is to find an algorithm which works in a polynomial time.
It only has to be hard one way and easy the other way.
no, I know. I'm talking about because I don't.
So the quantum computer would still have to understand how to approach this task. So
I thought the idea was that hypothetically, like a quantum computer could basically just like solve, like could take like every possible solution and just verify all of them, and then now it knows what. Like,
yeah,
the solution
it's similar
is
to
physically.
brute forcing. It's because it doesn't answer the question whether it's possible for all problems in NP to create a polynomial algorithm. So this is a mathematical task which has to be proven answer yes or no. For now, we don't know.
Yeah, exactly. It's the difference between the proof and being able to solve it. Because even if the quantum computer can generate the solution, it's still generating it by brute forcing the entire space.
I thought that's
And it brute
what.
forces it instantly.
I thought that's
that
what
is
they
P
were.
equal, then P equals NP completer.
Yeah,
Well,
no, just because of the definition of N and NP, but practically speaking.
Yeah. Moreover, if someone is able to find polynomial algorithm to find a solution for the problems which are used in public cryptography, it still doesn't mean that the entire NP equals to P. It would mean you can prove that P equals NP if you deal with an NP complete problem. This is the hardest problem of the NP class. They're proven to be the hardest one, and if at least for one you found a polynomial solution, then you proved that this is entirely polynomial, entirely the same as a polynomial. But those problems are somewhere in the middle. They are not NP complete. They are not the most difficult ones.
I was kind of curious, so you mentioned that symmetric was faster than asymmetric. Do you think you can provide a little bit of quantification of just how efficient it is?
It's
How
hard.
big a difference?
By the definition of tasks which are used in asymmetric, you can see that there are big numbers which are taken to the power of something which are multiplied by something, and the plain text which are used in the encryption scheme here. Here, the plain text, you take it to the power of the key. So if the plain text is long, imagine how difficult are calculations to take it to the power of a big key compared to simple binary operations of substitution, permutations used in block ciphers. So it's effective on very small data, but it's good to combine it.
Okay, yeah, maybe you could say that with asymmetric keys, you need to combine the two keys to get the result, whereas with symmetric keys, you only need the single one, and by definition, it's
There's fewer steps to the problem,
Yeah.
is really what it is. Yeah. So there's less math being done, which means it's going to be quicker calculation.
Are you staying for food?
Yeah?
Good. Take a peek.
Oh yeah, so are there still padding exploits? Just do padding exploits still happen?
It depends on realization because